From the dawn of humanity, the moon has captivated our imaginations. Its silvery glow has inspired countless myths, legends, and stories across cultures and generations. It hangs in the night sky, a luminous pearl against the velvety backdrop of space. Its phases mark the passage of time, guiding ancient calendars and agricultural cycles. But beyond its beauty lies a deeper significance. The moon is not just a passive observer in our sky, it plays an active role in the dynamics of our planet. The moon is our celestial neighbor, a celestial body bound to us by the invisible threads of gravity. This gravitational bond affects everything from the ocean tides to the stability of Earth's axial tilt. Understanding its distance is not merely an academic exercise, it is fundamental to unraveling the secrets of our universe. By measuring the distance to the moon, we gain insights into the mechanics of celestial bodies and the forces that govern their movements. The Earth-Moon distance, a seemingly simple measurement, unlocks a treasure trove of knowledge. It helps us understand the scale of our solar system and provides a reference point for measuring distances to other celestial objects. It serves as a fundamental yardstick for astronomers, allowing them to gauge the scale of our solar system and beyond. This measurement is crucial for calibrating instruments and refining our models of the cosmos. It underpins our understanding of tides, eclipses, and the intricate gravitational dance between Earth and Moon. The Moon's gravitational pull creates the rhythmic rise and fall of ocean tides, which have shaped coastal ecosystems and human activities for millennia. Moreover, this distance plays a crucial role in space exploration, influencing mission planning and spacecraft trajectories. Accurate measurements ensure that missions to the moon and beyond are successful, paving the way for future exploration and discovery. Throughout history, humans have sought to measure the moon's distance using increasingly ingenious methods. Early astronomers used simple tools and geometric principles, while modern scientists employ advanced technology and precise calculations. From the rudimentary observations of ancient astronomers to the laser-precise measurements of today, our quest to understand this celestial yardstick has driven technological advancements and deepened our appreciation for the cosmos. Each new method has brought us closer to understanding the moon's true distance and its impact on our world. As we delve into the history of these measurements, we embark on a journey through time, witnessing the evolution of scientific thought and the relentless human spirit of exploration. The story of measuring the moon's distance is a testament to our curiosity and ingenuity. Each measurement, from the ancient to the modern, represents a stepping stone in our understanding of the cosmos. These efforts have not only expanded our knowledge, but also inspired future generations to continue exploring the mysteries of the universe. In the absence of modern instruments, early astronomers relied on keen observation and geometric reasoning to estimate the moon's distance. These pioneers, limited by the technology of their time, laid the groundwork for future generations of astronomers. Their methods, though rudimentary by today's standards, demonstrate the power of human ingenuity and the enduring allure of celestial mysteries. One such method involved using the human hand to measure the moon's angular size. By extending an arm at full length and observing how much of the hand could cover the moon's disk, astronomers could estimate its angular diameter. This simple technique, while lacking in precision, provided a rough estimate of the moon's relative size. Another method exploited the geometry of lunar eclipses. By observing the time it took for the Earth's shadow to completely engulf the moon during a lunar eclipse, ancient astronomers could deduce the relative sizes of Earth and Moon. Combining this knowledge with estimates of Earth's circumference, they arrived at approximate values for the moon's diameter and distance. These early attempts, while imprecise, highlight the human desire to comprehend the cosmos. They represent the first steps in a long and fruitful journey to unravel the secrets of the Earth-Moon system.
In the 3rd century BC, I proposed a groundbreaking method based on the geometry of lunar phases. This was a time when understanding the cosmos was still in its infancy, and every new idea was a leap forward in our quest to comprehend the universe. I reasoned that when the moon appears exactly half illuminated, the Earth, Moon, and Sun must form a right triangle, with the moon at the right angle. This alignment, I believed, could unlock the secrets of the distances between these celestial bodies. By measuring the angle between the Sun and Moon at this precise moment, I attempted to calculate the ratio of the Earth-Moon distance to the Earth-Sun distance. This was a revolutionary idea, as it applied the principles of geometry to the vast expanse of space, bridging the gap between terrestrial and celestial measurements.
While Aristarchus's method was theoretically sound, his measurements were hampered by the limited accuracy of instruments available at the time. The tools he had were rudimentary, and the precision required for such calculations was beyond their capabilities. Nevertheless, his work demonstrated the power of geometric reasoning in astronomical observation and inspired future generations of astronomers. His ideas laid the groundwork for more accurate methods and tools that would be developed in the centuries to come.
Centuries later, in the 2nd century AD, I refined lunar distance measurements using a method known as parallax. This method was a significant advancement, building on the foundations laid by earlier astronomers. Parallax refers to the apparent shift in an object's position when viewed from two different locations. This phenomenon can be observed in everyday life, such as when you look at an object with one eye closed and then switch to the other eye. By observing the Moon from two widely separated points on Earth and measuring the slight difference in its position against the background stars, I could calculate the distance to the Moon using trigonometry. This method provided a more reliable and accurate measurement, showcasing the advancements in both observational techniques and mathematical applications.
Ptolemy's method provided a more accurate measurement of the Moon's distance than previous attempts. His meticulous observations and calculations marked a significant improvement in our understanding of the cosmos. His work, compiled in his magnum opus, the Almagest, became a cornerstone of astronomical knowledge for over 1,000 years. The Almagest not only preserved the knowledge of previous generations, but also served as a foundation for future astronomical discoveries, influencing scholars and scientists throughout the ages. Section 4, Galileo's telescope, a new era of lunar observation. The invention of the telescope in the early 17th century marked a turning point in astronomy, revolutionizing the way we observe the cosmos. This groundbreaking invention ushered in an era of unprecedented celestial observation, allowing astronomers to peer deeper into the universe than ever before.
Galileo Galilei, a pioneer in the use of this revolutionary instrument, was among the first to harness its potential. With great curiosity and determination, he turned his gaze towards the Moon, revealing details never before seen by human eyes, such as craters, mountains, and vast plains.
His observations shattered long-held beliefs about the Moon and the heavens, and paved the way for a new understanding of our celestial neighbor, challenging the Aristotelian view of a perfect and unchanging universe. Galileo's telescope, though rudimentary by modern standards, magnified distant objects significantly, bringing them closer for detailed study and allowing for unprecedented observations of the lunar surface.
When I aimed my telescope at the Moon, I was greeted with a sight that challenged the prevailing Aristotelian view of the heavens as perfect and unchanging. Instead of a smooth, polished sphere, I observed a world marked by craters, mountains, and vast plains.
These observations revolutionized our understanding of the Moon, transforming it from a distant, ethereal object into a world with its own unique topography full of geological features. The detailed sketches and drawings Galileo made of the Moon's surface provided invaluable insights, and these observations laid the foundation for future lunar exploration and study, transforming the Moon from a mere point of light in the sky to a tangible world with its own landscapes and features.
My telescopic observations not only shattered old paradigms but also ignited public imagination, fueling a surge of interest in astronomy and scientific inquiry, inspiring countless others to look to the skies. This newfound interest led to the establishment of observatories and the publication of numerous astronomical texts.
While Galileo's telescope did not directly lead to more accurate measurements of the Moon's distance, it fundamentally changed the way we perceived our celestial neighbor, opening the door to future discoveries. His observations paved the way for more detailed studies of the Moon, laying the groundwork for future advancements in lunar distance measurement and our overall understanding of the cosmos. Section 5, parallax triangulating the distance to our celestial neighbor. The concept of parallax, first employed by Ptolemy, was further refined in the centuries following Galileo's telescopic observations. Astronomers realized that by observing the Moon from distant points on Earth, they could significantly enhance the accuracy of parallax measurements. This realization led to coordinated efforts to measure the Moon's distance with unprecedented precision. In the 17th century, astronomers Giovanni Cassini and Jean Richet undertook a groundbreaking collaborative effort to measure the Moon's parallax. Cassini remained in Paris while Richet traveled to Cayenne, French Guiana, a location significantly further south. From these widely separated points, they simultaneously observed Mars against the background stars, carefully noting its position. By comparing their observations and applying trigonometric principles, Cassini and Richet were able to calculate the distance between Paris and Cayenne with remarkable accuracy. This measurement in turn allowed them to determine the Moon's parallax and derive a more precise value for its distance from Earth.